Thank you for spending time.
I'll see you tomorrow.
I get the sense this is a different way of doing things, and that's helpful.
Actually,
Yeah. Good. I'm glad to hear that. I'm glad that this is something different and gives us something different to try. Thank you, Oliver.
Thank you.
Dude. Weiss, that's in Heath, the far corner. Jared, it's like you're in some kind of science place or something.
Something like that, yeah.
Ben's on his way, but you are loud and clear, and everything looks good. How do we look to you? Aside from
Yeah.
off-center and backlit.
Things sound good, so.
Cool. Hey, Ben. Look, it's Jared, and he's someplace sciencey.
Whoa, science!
Where's Kira?
While we're waiting for other people to show up, Jared, you want to try sharing your presentation?
Yeah, let's try that.
And the only question I have, do you have video or audio in it?
Possibly. It's in the backup, is all.
Okay.
It doesn't need audio if that's the problem.
Okay, no, yeah, sometimes through the system, sharing this way, the video can be choppy. Is the video a YouTube clip or like a MP4 or something?
It's like an MP4. Yeah, it's probably something I won't get to anyhow, so
Okay.
Don't need to worry about it too much.
All right. And where's Kira? One second.
Ben said she might come in and watch class today because she has been to CERN. She was there in 2010, took her kids to go see it, and she's really excited to see it again.
Oh, really?
Yes.
Cool. Hey, Josh.
Hey, Ben.
Just checking. What are the rules on that?
That would be 5 would be your 5 is a discussion, but there's nothing.
Okay. All right, because a couple more 4s I need to enter in for next time. Are Peter and Limbo there, or they're just...
They set things up before I got here, so they are here in the school. I have not seen either of them in person yet.
Were they shrunk
there's
with some
Peter
sort of
walking
laser?
It's possible, but he's back to normal size. Peter's walking up in the background.
Oh, okay, good.
Is that you, Simone?
Yes.
Josh here. How you doing, man?
Not too bad. How you doing, buddy?
All right. Seems like you guys are out of Ed's office now. That's nice.
Yeah, we're gonna be back there next year, though.
Oh, you are?
It's gonna be our own office, though, hopefully.
Oh, nice. Sweet. You might be the first school to have their own MSO office. We just get classrooms.
Fingers crossed.
All right. All right, let me see here. I don't remember Jasmine or... Hey, Peter.
Hey, Mr. Taylor.
There you are. Got to zoom out. Hold on.
Oh, there we are.
Little far. Sorry, Jared, almost there. I'm surprised.
No worries.
I don't think I remember Trinity being absent today, and I can't imagine Jasmine wanting to miss this. Oh, there we go. Did you literally just log in?
Yeah. Yes. We heard it. We heard what you said about me.
Okay. That was funny. All right, so we're missing, is Limbo here, Peter?
Yeah, he's here.
Okay. Limbo, we got Henry and Coleman, we got Dalis and Post. Missing, MPH. And, all right. So everybody, thanks for coming. We only have a few days left. So presentations from you guys are going to start again on Friday. I'll be in touch via email so we can wrap those up. But we still have left Coleman and Will, Jasmine and Kaylee, and Kira and Peter. But we have several days to do that in. And just to make sure you guys are aware, we are just doing final presentations. I'm not sure if you had any question about this, but we don't have a final exam. This is it. Okay. We will have class on the 4th of May. We'll probably be wrapping up the final presentations. And then on the 8th, we may have spillover depending on if people run over, but probably we'll just be able to kind of say goodbye and go our separate ways. But for now, my friend Jared Vasquez is not in America, and all kinds of science is happening, apparently, behind him, and I think he wanted to talk to us about the Large Hadron Collider and things related to it. Does that sound good, Jared?
Sounds good. Cool.
All right.
So, yeah, I guess I'll just start off by saying, so I'm here at CERN. I'm extremely jet lagged because I just got here the other day, and it's been a really intense week. But anyhow, I set up my whole setup here in some place very sciencey. So behind me is actually like a life-size version of the competition called the CMS detector. In my talk, I'm going to talk about what I actually work with is the Atlas detector, which is twice as big. But that's our bragging rights. So yeah, lots to go through. I'm just going to warn you, I tried to slim these slides and I didn't want to cut too much content for you guys. I also wanted to give you guys a chance for lots of Q&A. So I might run up right on the time. I'm going to try to go through these as quick as I can. But if you have extra time, I'm happy to sit here an extra 10, 20 minutes and answer questions. So
do you want like a 10-minute warning?
Yeah, that'd be good. And then
Okay.
I'm going to try to get through this as quick as possible anyhow.
All right.
So yeah, let's just start then. Higgs boson in the universe. Why do we smash things together at the LHC? Okay, so basically everything I'm going to be talking about today is, and just to double check, you can see my slides, no problem?
Yep.
Great. Okay, so everything I'm going to be talking about today basically boils down to the standard model, and it's the best tested theory pretty much in all of physics and existence. It just passes pretty much every test with flying colors, and it's an incredible thing. And so you're going to learn more about this, but this pretty much describes you all of particle physics. So let's just work our way up there first, though. So I'm not going to tell you guys about F equals ma. You guys know this very well. But let's talk a quick review about what happens when things move really fast. Right, so there's this guy, Einstein. He comes around, writes this equation, E equals mc squared. And this is cool because now this means mass and energy are related. This is also c, the speed of light, right? And basically, he comes and makes these postulates and says nothing can move faster than the speed of light. And if you do move as fast as the speed of light, you have to have zero mass. Okay, but this isn't the whole story. So the full story is actually this full equation now. It's E squared equals mc squared squared plus pc squared. And so what this is actually telling you is that the faster that you're moving, the more energy you have as well. And so we can use this at the LHC. Okay. So just keep that in the back of your mind, and we'll come back to that very soon. Okay. So what are things and what are they made of? You all know this periodic table. The universe is pretty much made out of atoms, and everything we see in existence and we interact with them day to day can be organized in this periodic table, and it can tell us a lot about things. Right, so you take your monkey or a person, and you can look very, very close at it under a microscope, right? And you find out, hey, these things are made out of cells. And then you can even look further into that and say, hey, what are these cells made out of? And you find out that they're made out of atoms, right? Well, it's not just living things that are made out of atoms. It's also inanimate objects as well. Carbon, coal, diamond, right? They're also made out of atoms. So you can keep playing this game, right, and ask now, what is an atom made out of? So just probably a review again, but what's smaller than an atom? So you have atoms made out of protons, neutrons, electrons. But what you might not know is your proton and neutrons are actually made out of quarks. And so the neutron is made out of an up and two down quarks. And these are all kind of held and bound together by these things called gluons that kind of interact and mediate between them. The same thing can be said about a proton, except instead of an up and two downs, it's a down and two ups. And again, it's held together by gluons. You can try to look smaller at an electron, but this is actually what we call a fundamental or elementary particle. So these are really like the building blocks of the universe. As far as we know, you can't get any smaller than an electron. It's not made out of anything. Same thing with these quarks and gluons. As far as we know, and to very, very good precision, they're not made out of anything else. So this is really what we're trying to study with particle physics. Okay? So just like the periodic table, we can organize all these fundamental particles into a nice little table that tells us a lot of information about it. And this is really what's described by the Standard Model, right? So here's all our particles, great. And there's one addition now, which I'll get to, is the Higgs boson. And so this table is organized by mass and charge and spin and all these fundamental properties, right? And there's fun little properties like take the proton, for instance, right? It's made out of two up quarks, so that's charge 2/3 times 2, 4/3, and a down quark, which has a charge minus 1/3. So you added all that up and you get a +1 charge. The neutron, on the other hand, is up and two downs. Add all those up together and you get a 0 charge. So these things build up on each other. And by understanding what's really, really small, you can start to understand things that are a little bit larger. And you can even understand fundamental things about our universe, Big Bang, things like that. Cool. So what else do these particles do? Well, let me just explain how this table is organized a little bit. This first column here is what we call the first generation of fermions. This pretty much makes up most everyday matter, right? You have those ups and downs that I was talking about. They make up the neutrons and protons. You have an electron, and then you have these neutrinos, which are very, very strange, and you interact with them every day, but they're a whole story into themselves, right? Then you have this far right column. These are the force carriers. They're called bosons, and basically you can think of them kind of like a medicine ball in a way. If you hold like two charges apart from each other, right, they're going to repel without ever touching each other. The reason they know to repel each other, they don't have ESP or some kind of psychic power. They can't see the other charge. But what happens is they send this force carrier back and forth like a photon. So you can kind of picture this like the medicine ball in the picture. One electron throws it at the other one. He catches it, moves a little bit further. Then he throws it back. They keep moving apart from each other. And these are really how particles interact. Then the things in the middle, we can create them artificially. Some of them come into our everyday lives just from cosmic rays and stuff. But really, what's interesting about them is they're what made up the universe in the fundamental moments right after the Big Bang. And beyond that, they don't really have too much use to us. But by understanding them, we can start understanding more about our universe and its origins. So, right, this is a lot of information, but another thing to note about particles is most of them aren't stable. They decay. So if I just go back to this table here, right, most of these particles in the three right columns all decay into something into the first column there. There's a couple exceptions, but not many. So you can take this Z boson, for instance, or the top quark, and it'll decay into something smaller, and that will decay into something smaller until it gets, to an electron or up and down quark, and something that makes up most matter. So this is actually really how we see particles by using these decays. And Another interesting things about these decays is they don't always decay into the same thing. A Z boson doesn't always decay into muons. It sometimes decays into electrons. Other times it decays into taus. Other times it decays into quarks, which we call jets. And it's purely quantum mechanical. It's just a probability of what will it decay into, and it's really an interesting thing. And we can describe all these things and understand them and predict them using these funny little scribbles. We call these little scribbles Feynman diagrams. So let me explain these real quick. And by the way, this is a lot of information coming at you very, very quickly. It's just a very quick review, and hopefully I'll make some sense of it in a minute. So you have this Feynman diagram, and it looks like a bunch of funny scribbles, but actually this follows a very, very sophisticated, like, mathematical machinery. If you were to look at this equation as a particle physicist, this actually represents several really complicated integrals. They're called path integrals, and they're integrals over all paths that a particle could take in space-time. So at different times and in different paths in spatial dimensions as well. And each one of these lines represents something. Each time the lines touch, they represent something else. It's very, very complex. But what you can really take away from these diagrams is kind of not physical. It's a mathematical model. So really the best we can say is, well, things come in, magic happens, and then stuff comes out. So here you have quarks from the proton-proton collisions. Magic happens, and out comes a bunch of other quarks and leptons and neutrinos and things that we can see in our detector. Okay, so let me start trying to make a little bit of sense out of all this and tying it together. And I'll start by doing that by saying, how do we see these particles? So let's say you have an unbreakable iPhone, and you want to know how this thing works. So to understand how it really works, you want to open it up and get inside. There's no tool that can open it, and it's tougher than anything else. How would you open it? Any ideas?
Good. Limbo, Peter?
Yeah.
Are you going to answer the question, Limbo?
I don't know what's going on. I just came here, sorry.
No worries.
What would you do
hit it with another one. Yeah.
Is that Kaylee?
You should hit it with another one of it.
Very good. Right, exactly. Because if you threw anything else at an unbreakable iPhone at anything else, it's just going to break through it, right? So obviously the answer is to throw two of them at each other. So that's pretty much what we do. And out you see all these chips and cameras and all these little things coming out. And by looking at the things that come out, we can really understand the iPhone and kind of piecing them back together. Unfortunately, you get different things out every time you throw an iPhone at each other, two iPhones at each other. So you got to have a lot of iPhones and just keep throwing them at each other really, really quickly and trying to make sense out of it from there.
This might actually be more expensive than the LHC.
You'd be surprised. So this is basically what we do at the LHC, except instead of unbreakable iPhones, we have unbreakable, composite particles, these protons that are very, very hard to break apart. So we need to do it with a lot of energy. Yes.
Can you use we can see your mouse over. Where are you on this map right now?
Where am I? Great. So I am right here. So yeah.
Go ahead.
This is an incredibly large machine. It's the biggest machine in existence, probably the most expensive machine ever built, I think is another criteria. There's a lot of firsts. There's a lot of record holding here. It's 17 miles around, 27 kilometers. It's basically 2 football fields underground in some of the deepest parts. And it's just really an incredible machine. So all around this 17 miles is basically really, really good magnets, superconducting magnets, all focused around very, very precisely to take protons and just focus them and spin them around as fast as possible. and then collide them together. And so there's just an incredible amount of engineering and work here. It's also in a very, very nice location in Switzerland where I am now. We're very, very close to the French border, so you can see this white dotted line is actually the border to France, and over here is Switzerland, over here is France, and if you go far enough, you're in France again. There's a beautiful lake. You're right between the Alps and the Jura, so if you're here in the winter, there is some great skiing. If you're here any other time of the year, there is great hiking to do. And it's just a great place to be. You attract people from all over the world. There's at least 100 different nations represented on site at any time, and you get friends from places you never expect, like Iran and Iraq and Nigeria, right? So it's pretty cool. I just want to show you again how big is this thing, and I'm just going to project it over New Haven so you can get an idea of that. So this is the LHC built in New Haven. It pretty much takes up all of New Haven, going into West Haven, Fairhaven, and quite a bit of ways. So this thing's huge.
And just so you know, on the left there, if you go back, the Maltby Lake's there, right, kind of on the circumference of that circle. That's Hopkins.
Gotcha.
Which not all of these people know, but that's where we are, is right there by those lakes. Go ahead.
So there's different detectors here. I'm going to be selfish and just talk about the one I work on. The one our competition is behind us. It's also okay, I guess, but we're better. So here's the Atlas detector. It's buried two football fields underground. This thing is huge, right? So just for scale, there's two little people. I promise they're not incredibly short. They're probably very tall people, the German or something, right? This thing is about 6 stories, 7 stories tall. It's the size of Notre Dame Cathedral is pretty much the exact dimension. It's really just gigantic, and it's completely made up of like microelectronics, just all squeezed in together, packed in as tightly as possible to just kind of work as this great detector all together. So there's just billions and billions and billions of channels trying to all synchronize together, and we use this to try to just take little pictures of events, basically, particle interactions. Part of my job is really fun. It's actually to fix the detector when it's not working. So these magnetic fields will be on, and I need to crawl in between these tiny little gaps in the detectors. And with the magnetic fields on, you typically have a dosimeter that's floating in midair and things like that. So it's a lot of fun. So just to explain what this thing is actually doing, you can basically think of it as a giant digital camera. When I say all these channels working together, basically you can think of them almost like a micropixel. Of course, this isn't a traditional camera. It's not taking just an image. It's more like it's taking a 3D image, and it's also measuring things about the particles as they pass through them. So charged particles will pass through material, and they'll be deflected by the magnetic fields a little bit. So that allows us to measure the momentum of a particle. Things like photons, we crash them in at high energies into certain materials that'll make them shower into electrons, like a photoelectric effect, and then we can measure basically the energy of a photon's jets or the quarks. We do similar things and using all these like materials, we can pretty much reconstruct all these particles and understand, after we threw these protons out together, what came out of it. And this is how we do physics. This is how we look for the Higgs boson. The only thing that we can't really see is a neutrino. Again, they're a very, very different beast. Right, let's just smash things together. Here's the protons. They're colliding. I'll remind you, once they collide, magic happens. Stuff comes out. These particles decay, right? And so all that we see in this digital camera is we see these things that come out of it, these decay products, and we can try to reconstruct them back together and figure out where they came from, right? So this all begs the question, right? I thought we were colliding protons together, so how do we actually make some new particle? This is where I can come back to where we started at in the beginning of the talk, this whole E equals mc squared, right? Basically, the E equals mc squared is key to this whole thing. Also remember that plus pc squared term. So the faster we collide these things together, the more energy we have. So we can take the two protons, speed them up as fast as possible, 99.99999% the speed of light, and this creates a tremendous amount of energy, right? Then we smash these two particles together. This energy is now all free to turn into mass. We completely annihilate the mass and turn it into energy. Now it's kind of like a particle cafe, or buffet is maybe a better term for it. You have this menu of particles that exist, right? And you can basically order anything on the menu as long as you have enough money. You know, proton collisions are very, very greedy. They like to spend all the money that they have. So let's say we crash these two particles together with an energy of $300, right? In the particle world, this money is like energy, right? So we call it GeV as a unit. So with 300 GeV, we have enough money to basically order 2 Higgs bosons, maybe a couple tau particles. Gluons are actually free. They're kind of like the breadsticks. You can get a whole bunch of them coming out of there. And you just get a bunch of particles in there. Unfortunately, again, proton collisions are very greedy. They try to get the most for the money, so they tend to order things that are cheap. Because of this, you get things that are heavy, like the top and the Higgs boson, very, very rarely. And so this makes it a little bit more difficult to find the Higgs. So you have to do these collisions very, very rapidly. In fact, we do them every 50 nanoseconds, so we get several billion collisions every second. So how do we visualize all of this information, all of these like billions of pictures a second? There's a tremendous amount of details in this, and I can't go into any kind of depth. But I'm just going to try to sketch out a picture, right? You have this front-end detector, and it's got all these microelectronics on there trying to decide, is this interesting or not? And if it decides it's interesting, then it's going to send it to a computer and a trigger system, right? And that's going to just do a little bit higher level information. It's going to say, is this really interesting? Okay, maybe. If that decides it's interesting, it's going to keep forwarding it to sets of computers, trying to process this information as fast as possible. Unfortunately, we can't, keep up with all the information that we're getting. So it's really important we try to throw out things that just aren't interesting to us. And that pretty much means anything that we know. So we look for things that are interesting, something new, and just try to keep that. So it just has to go through this huge array of computers. A lot of these things are really, really slow. You just have billions of channels you're trying to reconstruct into these big 3D pictures with all this high-level information, and it takes some time. So we just try to store it as quick as possible, reconstruct it, and usually it takes several months to actually see this data after it's been collected. In the end, we have nice processed data, which we can, plug into our computers. And if our computer is being nice to us that day, it will actually give us some results, and we can interpret this with histograms, which tell us a lot of information and is really our bread and butter of analysis. So let me just kind of give you an idea of how we can use histograms now. So there we go. So I'm going to show you a roster of students in the right? And they're all from grades 7 to 12. And I'm going to give you 3 seconds to tell me how many students are in the 7th grade, okay? So just get ready. 3 seconds starting now. Great. So who thinks they have the answer?
No.
No one. Okay, good. So there's a much better way to interpret this information. Instead of maybe like looking at the roster and trying to count it each time, maybe at the start of class, I just give every student a ball, right? And I have these different buckets set up, and each bucket represents what grade are you. And I just ask the students as they come in the door, throw a ball in the bucket that they correspond to. So they start doing this, right? And these things just kind of stack up. And now you can tell basically really quickly how many students are in the 7th grade, where are the most students at, what grade, where's kind of the average, et cetera, right? So you can see most students are in the 7th grade. There's 4 of them here. The second largest population is 9th graders, things like that. And, if without using this analogy of balls, basically this is the whole idea of histograms. You kind of just stack up bars, keep counting things, and you kind of keep the counts in different categories and tallying them up. So this is really useful, right? You can do this not just with like discrete things like a grade number. You can do it with like something that's more continuous, like how much does a student weigh? So you can just set ranges for each bucket. Say if you weigh 100 to 110 pounds, throw your ball in the first bucket, etc. Right? And using this, you can really quickly see where's the mean, where's the mode, and you see, most students are probably around 125 pounds. So this is basically what we do with particles. We can get all this high-level information from our giant digital camera, kind of reconstruct it into ways that the computer can turn these things into histograms. And so this is what we do with a lot of particles. This is what we did with the Higgs. And here I have an example of the Z boson, which is something that was discovered a long time ago, but is just something we see a lot and take for granted nowadays in particle physics. So you can take the decay products, like the 2 muons I showed earlier, decaying from the Z boson, just kind of add those 2 things back up and figure out what's the mass of the particle that they came from. And these things will peak up nicely at 91 GeV for a Z boson. That's the mass of that particle. And it's got a little bit of a range, and you can kind of relate that to like a Heisenberg uncertainty principle. Great. So how does this whole mass thing help us find new particles in physics? Well, the first thing to remember is all particles are identical. There's not fat electrons and ugly electrons. There's just electrons, and single thing that is an electron is exactly the same. They always have the same mass, and that's why you get these peaks right at that single place. So we can take this information and use it to our advantage. So what we do is we simulate the things we know about. We call those the backgrounds. This is all the physics we know. We've learned it in the past, and we know it so well we can actually model it on our computers. So we do this. Here's our background. Here's what it would look like. Great. Now we go to a theorist. He'll tell us, we know this about particles. We know this about particles. Maybe there's this thing that exists. And taking what we know, we can simulate something that we think might exist, like the Higgs boson. So now we have our hypothesis, and we can kind of just lay that on top of the background. Now this is the most important part. Let's look at the data. So we can get data points, these little black X's, right? And just seeing where do these things line up with? Do they align with the background, or do they align with the background plus hypothesis? If they align with the background plus hypothesis, then maybe you discovered something, right? On the other hand, and more often the case, usually these data points just line up with the background. This isn't a bad thing, though, right? It's not as fun, but you still learn something. You know that your idea, this hypothesis that you had, is not really true, right? So you've excluded something. If you think that a graviton exists, or even the Higgs boson exists, before a couple years ago, and you find out that your data does not match the background, or match the hypothesis, then you have to get rid of it at some point, right? So the universe is basically telling you you're wrong. So let's apply this all to the Higgs boson. Before I move that, is there any questions about this? I'm moving very quickly, but.
What up, peeps?
Good. All right. So let's apply this to the Higgs boson. Before I do that, let me just tell you really quickly, why is the Higgs boson important at all, though? What does it even tell us, right? So the go-to question is Higgs. Why do physicists call this the God particle? Well, we don't. This is just basically journalism. So the standard model that we talked about in the beginning and through a lot of this talk, right, is basically all understood in theory in the 1960s. And the only thing that was wrong with it is if you try to add any mass to these calculations, all of a sudden everything broke. If you pretended like particles had no mass at all, then things worked great and they predicted pretty much everything. So this is a big problem because we know that things have mass. So this was all worked out by Peter Higgs and others, and they predicted this Higgs field that would interact with elementary particles and give mass to them. So here's a picture of Peter Higgs, the theorist, not to be confused with the boson. So let me just explain how this field works. It's this concept of a field, you can kind of think of it like an electric field, right? It's everywhere in the universe. You just can't see it. So let's just do this through analogy. Imagine a field of snow where everything's pretty much evenly distributed, goes on forever in every single direction. So here's our Higgs field. Now, particles interact with it differently, right? A particle wearing only like boots is going to interact with this snow very, very strongly. This means it gets a lot of mass. If you've ever, crawled your way through a lot of snow, you've definitely felt the snow kind of pulling on you, and you feel a little bit heavy. And that's kind of what these particles that are wearing boots are feeling. They're crawling through this Higgs field, and they're feeling very heavy, and so they're acquiring a lot of mass. If you're a particle and you're wearing snowshoes, on the other hand, you're interacting with the snow a little bit less. It's not as hard to crawl through this Higgs field, and so you still have some mass, but not so much. Now you have particles who are very smart. They're wearing skis, and they interact very, very weakly with the snow, and they just kind of glide right through it, and they get very, very little mass. And then some of them, I don't know, they have hover cars, and they just go right through the snow and don't interact with it at all, and they would have no mass at all. So there's this question of how did I get into this discussion of a field if we're talking about a particle, right? Well, so in my analogy of snow, you have to remember that snow is really made out of snowflakes. And similarly, you can think of the Higgs field as being made of like Higgs boson particles. And when you excite this field, a Higgs boson pops up. And so if you imagine a universe where you can't see this field of snow, the analogy kind of plays with the LHC of, well, if you can't see the snow, you can see the snowflakes at least, or even if you can't see the snowflakes, you can see water. So when these snowflakes melt, their decay products come out, and you can see that, well, this water's coming out. Maybe you add up that water, it reconstructs to a snowflake, and you can prove that the snowflake exists. And if you can prove that a snowflake exists, you can prove that snow exists too. So this is the best analogy I can come up with, but hopefully it makes a little bit of sense of why the Higgs boson is so important. So basically what it's saying is if you can find a Higgs boson, if you can prove that a Higgs boson exists by looking at its decay products and saying, hey, there's this big mass, by proving that a Higgs boson exists, you've proved that the Higgs field exists. And if that exists, that explains why things have matter. And this was something that this otherwise, very successful theory was lacking is now completed. So yeah, the Higgs boson makes particles fat. So does that analogy kind of make some sense? Is there some questions before I put this all together?
Some questions I think for the end, but I'm good.
Okay, cool. So let's just again, lots of information, but let's just put this all together. Let's do the experiment. Let's find the Higgs boson. Let's use these histograms by taking our decay products and reconstructing them, and let's prove that the Higgs boson exists. And again, if it exists, then great. We have a Higgs field, and we explain why everything has mass. So this all happened July 4th, 2012. And let's just pretend we're there. And this kind of animation, hopefully you can see it well enough, is just going to be a time lapse of us taking data. And on top of that data is going to be our prediction of the background. What do we expect to see on all the things we know? And there's also an expectation of, based on how much data we have, how often do we expect the Higgs to be there? So that's plotted on there, our hypothesis. And what we want to see is our data matching this background plus hypothesis, and that would prove the Higgs boson exists. So here's us taking data. And as we take more and more data, there's just more events filling up in these histograms, right? And you're starting to see things grow really, really quickly, all this physics we know. But if you look in the middle here, things are starting to get a little bit away from the blue line. So let's look at our signal plus background, our background plus hypothesis. If you look at that, you see that it actually matches the data very, very well, right? And so using this, you can kind of quantify it with some statistical values and say, wow, we found the Higgs boson. This isn't a fluke at all. So let's just look at it one last time. So while taking data, most of the time it matches the background. But once you have enough data, you can see this really, really rare process that comes in, our signal, our hypothesis, and that's our Higgs boson. It's just sitting right there at 125 GeV, and you can see it popping up over everything else. So this is really how we discovered the Higgs boson. We can do this in multiple channels by looking at different decay products. The one that you saw there is when a Higgs decays to 2 photons, so two particles of light. We can also do that with like electrons, 4 electrons, for instance. So here's a quick idea of what it'll look like. Over here's that Z peak I showed earlier. Here's another crazy stuff going on. And over here, the data is going to match the Higgs boson hypothesis. And so when we collect data, most of the time things just look like our backgrounds. It looks like all the physics that we know and just expect and we're bored with now. But if you look what's going on here, you start noticing the data is getting away from these backgrounds now. Something weird's happening, something that we don't quite understand. Right, so we can look at our hypothesis, our Higgs boson, and kind of fill that in. And when we look at our hypothesis, we find out, hey, wow, this hypothesis actually fits our data pretty well. And again, we found the Higgs boson in another place. So congratulations, you guys have just done all the experiment. So there's just the question of, is this all now? Is my job completely done? Am I homeless? Well, the answer is no, right? There's still a lot to explain. The standard model is really, really successful for explaining everyday things that happen, right? But there's a lot that it doesn't explain. It's not totally complete. There's a lot of extensions that need to be available. You might have heard about dark matter. It's been observed in the universe, right? Gravitational lensing. There's no explanation for this. There's dark energy also, which keeps the universe expanding at a faster rate than you'd expect it. Lots of new things like this, and we can't really explain it in the standard model. So we know there has to be an extension, and there's probably a particle physics explanation to dark matter and other things like that. So these are things we can keep looking for and trying to understand our universe. So yeah, that's all I got. So hopefully I can answer some questions, and hopefully that made a little bit of sense for you all as quickly as it was.
Thank you, Jared. I had a question, but Jasmine, you had your hand up. Go for it.
Oh yeah, I had a question about like the data. So like you were talking about how like the first graph where you saw like the hypothesis bump match up with your thing in the data, and how it was like when a boson splits into two photons. How exactly do you guys figure out like, well, these two decay particles came from this thing? Like, how do you figure that out? That they're not just like two photons from something else?
Yeah, it's a little bit complicated, right? So there's kind of two approaches to do this. You can talk to a theorist, who's going to do a lot of math and try to predict something that he thinks might exist. And he'll tell us like, well, if this particle exists, sometimes it's going to decay to 2 electrons. And so we'll look for events that have 2 electrons in them, and we'll just make vectors out of them in 4-dimensional space-time. And with those vectors, we can add them up and figure out the mass. So we can take a lesson from theorists. There's another way to do this, and that's basically we can just guess. We can say, hey, nobody's looked for something that's came out of 3 leptons before. What if we took 3 electron events and added all those up together? Is some particle going to be predicted? And sometimes we're surprised. We find something there.
So it's a matter of kind of like a key signature, almost like that those energies, when added together, don't add up to any other known things on the background. Basically,
yeah, right. So like in the Higgs boson case, it does add up to. There's still background in that region, but if you have enough data, your signal should be significantly different from that background also. So you can use these complicated statistics to really quantify that and say, is this just some statistical fluctuation from our background, or is this something that's real? And we're really, really careful about it. So it basically has to happen with a probability of like 1 in a billion to be considered real.
Other questions, guys?
Yeah.
What did you do before you worked with Atlas?
I did so I've worked with Atlas for a long time. I started it as an undergraduate, like my sophomore year. But right before starting that, basically I came to one of my professors and I said, hey, you do particle physics. I want to do that too. And he gave me a job. And before starting on Atlas, because it was just starting at the time, there was another experiment in Fermilab. It's basically used to be the largest collider in the world, and the experiment was called CDF. So I did a quick analysis there, kind of proved that I was worthy enough for Atlas, and then started here early.
I think Jasmine and Will also had hands up.
Yeah.
That was my question. So.
Oh, okay.
Cool.
So I'll go yes. Why exactly was it that like if you find a Higgs that proves there's going to be like a field, like why is that? I don't get that jump.
Right. So I kept it a little bit vague, and that's why. You're right, and there's a lot of work going on to this right now, right? So we definitely found a new particle, but we still have to study this particle in depth. So if in this whole theory that predicts the Higgs field, it also predicts a lot of really specific things. Like it predicts that the spin of the particle is 0. So there's no spin. That's something that doesn't exist in other elementary particles. The other particles all have a spin 1/2 or 1. So this is really odd. And so with a little bit more data and sometime soon, we can measure the spin of the particle and say if it's 0, is it 2, is it 1, is it 1/2? And so this validates it a little bit more. And so we can look at it into a really in-depth physics, really like precision studies of what's predicted by this theory and see if everything matches up. So it's possible that, in 5 years from now, we find something that doesn't match up with theory, and maybe that points us to some new physics that we never understood. Or
So this is just a first step in saying that it really is a Higgs boson.
Yeah. So when we first discovered it, they said it took a year for them to even say the Higgs boson. They called it a Higgs-like particle or a Higgs-like boson, even something like that. So we're pretty conservative with it, and this is going to be something that's studied for a long time before it's really believed. Yeah.
So what do you do? Like, what does the job at Sohn entail?
Right. So I do a lot of things. A lot of it, to be honest, is what you kind of see with these histograms. It's a lot of programming to take all this, basically giant spreadsheets and databases of information and kind of pretend like Google, right? We need to take all this information, come up with clever algorithms to sort through it all, and kind of select the things that we want from the things we don't want to do these analyses. So there's a lot of programming to make these kind of histograms and stuff like that. That eats up a lot of time. There's, of course, like other things that you need to do physically on the detector. So you need to sometimes go in there and replace boards, work on, new upgrades for the detector. Sometimes you just need to fix things. There's a lot to be done. So it's a mixture of analysis, engineering work, design, really just being hands-on with electronics, things like that.
Jasmine?
Yeah, and so far you guys have only found like the decay particles of the Higgs boson, not like the boson itself. Okay.
Right. So we will never see the boson itself. It's lives for a very, very, very short amount of time, and it's the more mass you have, the shorter it lives. So that's the only thing we'll ever be able to see. Things like muons, they have less mass. They live for a long time, at least in relativistic frames, and then you have a chance of actually seeing them.
So just get on a spaceship and travel at 0.99999c and watch back to the event, and then the Higgs boson will live longer. I mean, why didn't you just do that, guys? We were on board. I don't know where you.
We're spending too much time in our anti-gravity chambers here,
That's right.
So.
That's right.
Launch the LHC into space.
We would love to. So there's a couple of really cool experiments. They're basically like mini versions of the Atlas detector strapped onto like the ISS, and really? They just kind of sit there in space and measure particles, coming from supernovae and things like that. So there's cool things to do.
Little synchrotrons or just little Atlas detectors?
They're like little trackers, little calorimeters, things like that. Okay. So there's the 8, which is on the ISS. There's also a telescope called Fermi. It's basically a tracker strapped onto a rocket and then set into orbit. And so you can just measure track particles.
Cool. Do you know anything about the particle accelerator that was supposed to be built in Texas?
Yeah. So it was. I'm not sure what the final energy was supposed to be. I think it was supposed to be like even larger than the LHC. I think it was like 17 TeV, where we're designed for 14 TeV, something like that. But you probably saw the Particle Fever documentary. There's a lot of controversy around it. Politicians tore it up. Unfortunately, a lot of scientists also kind of tore it apart. A lot of the condensed matter experimentalists at the time, I guess, kind of believed that, hey, if we shot Ben should hide, they kind of believe like, hey, if we kind of shoot down this big project, maybe we'll get the money, and a lot of them came out with that. Unfortunately, that didn't work. When they shut down the project, the money kind of just disappeared with it. So.
Sorry.
it would have been before my time anyhow. So I was glad to be here when they discovered the Higgs. And
I feel like I remember hearing about it when I was younger, and that it was already being dug when it was shut down too. I'm not sure about that though.
They kind of commissioned it.
Oh, okay, never mind. Jasmine and Will, go ahead.
I asked a ton of questions. Will can go.
Well,
okay, mine's not really physics related, but why is it built in 2 countries?
So basically CERN was founded like right in the 1950s, like shortly after the World War II, right? And so it's the Central European Research Nucléaire, which they've renamed now. It doesn't even spell CERN. It's like Organization European Nuclear Research. But basically this was found by like 13 European countries kind of all collaborating together, and it was kind of a way of healing wounds after World War II, and especially after the race for an atomic bomb. You want these physicists and scientists working like really closely together and really sharing their expertise in a peaceful environment again. So sharing it between 2 countries is one way to do that, and it's really right in the middle of Europe if you ever look at it in a map.
And so I was gonna ask, you mentioned a couple times that you about neutrinos being really weird and stuff. So
they're totally weird.
What's your general take on neutrinos? I guess or pointing to the direction.
Neutrinos are awesome. So as soon as I'm finished with my PhD, I will I'm almost certainly going to start doing neutrino research. There's a lot to learn about them, and there's not too much theory that actually tells us anything. So by studying them, we can presumably learn a lot. It's a whole other talk by itself, but neutrinos come out of our sun all the time, so you can study them pretty well, and you're being bombarded by them by the billions every second, and they're not even interacting with you. And so they basically pass through the whole universe. They pass through galaxies and stuff without interacting with anything. And so they're totally weird. They change from one type of neutrino to the other, just oscillating. It's just something they do.
There's Jasmine, I don't know if you've seen it. There's a PBS documentary called The Ghost Particle.
No.
Look it up. I think it might be.
I think I saw the last 10 minutes of that one time. I heard about it.
It's a little dramatized, but it's still pretty good, and it talks a lot about neutrino oscillations between the different kinds, and it tells this really heartrending story of the physicist who predicted that neutrinos did have mass and did experience oscillations. So that they have mass, which means they experience time, right? Because they're not traveling at the speed of light. And so since they experience time, it would allow them to transform from one to another. If they travel at the speed of light, they wouldn't be able to. And so since there's 3 flavors of neutrinos as they float from the sun to the Earth, if they experience time, they would change into all these different kinds. And the neutrinos from the sun are only one kind. So when they got to the Earth, if you're only counting that one kind, you expect to actually find only 1/3 that number. Because they've turned into the other 2 flavors during that time. And so this physicist predicted it, and the experiment eventually happened that proved him right. Nobody believed him. And by the time, I think he won the Nobel Prize for it, by the time he was vindicated, he had Alzheimer's. And he's in the documentary. And he's so happy, and he did get to know that he was right, but he was pretty ostracized by the entire physics community throughout the entire thing. And it was both heartwarming and really sad. It's a decent documentary. It's not perfect, but it's pretty good. I used to show it in this class, in my brick and mortar version of the class. Anyhow, sorry.
Yeah, there's no. That's. I haven't seen this documentary, so I'm gonna check it out now. So
it's cool. It's cool.
So like I was saying, they pass through these galaxies without even interacting with them, right? So this is something that light doesn't do, and so it's. If you can detect neutrinos, they kind of work as a really good telescope also. They can tell you things from the Big Bang and the farthest depths of the universe without any kind of distortions. And so they're really interesting things,
awesome.
Physically as well.
My question is a physics one, and I don't know if if you can answer it without having to like explode math all over the place. But obviously particle fever focuses a lot on the disagreement over the two masses that they expected for the Higgs boson, and then the result of it being in between those two values, one of them more aligning with supersymmetry and one aligning more with many worlds or something like that, and it being in between seems, I don't know, it feels very dramatic. And what about the mass that was found and the two masses that were like largely talked about in media that were expected? And the fact that it lies in between them. Do you have anything to say about that, or is that all drama?
I would say the thing to keep in mind is, A, they're trying to tell a story. B, this was produced by a theorist. So the theory community is going to want it to converge into one of their nice models and vindicate themselves. From the experimental point of view, most of us don't think that the theorists are as smart as they think they are. I almost find it really satisfying that it falls right in the middle. So
would you say it's not as clear a distinction as they suggest in the movie, that like if it had been that one, it would have been like supersymmetry all the way, and if it had been the other one, it would have been like, oh no, it's been.
It motivates supersymmetry if it does, but at the same time, it could be a total coincidence.
Okay.
Right. So this is. When you look for particle in different masses, you really need to look at a whole range of masses and look for it there. And, sometimes it just pops up where you least expect it, and that's pretty much what happened with the Higgs and why it took so long to find.
I'm gonna seize the last question as well, but this is on behalf of everybody. And you guys were already kind of pushing at this question, but I think I've told them about my experience in this. But you were an undergrad, you were studying physics. How hard was it? For you to get into the lab, how hard is it for you to find a professor who's like, yeah, sure, come on, let's go, as a physics major?
Yeah, I think I really lucked out. My advisor was, he had some extra funding and he was really generous with it, and he was just a great mentor. He basically let me do my own thing and just kind of nudged me when I needed it. I don't know how easy that is all the time. But there are a lot of universities that are willing to take like undergraduate researchers and let them work with them. And, comprehending this stuff is actually, and starting to get some work done is actually really simple. It takes a few years to learn the hard theory and a lot of details. But my first year, I also went with an economics major who took my professor's class and, basically said like, hey, you're pretty good at dropping balls. Why don't you come to CERN and do some particle physics? And he did a great job. He learned how to program while he was here and learned a lot and contributed to analysis.
Yeah. Okay. Well, thank you very much, Jared. Thank you guys for showing up. If you guys have any more questions for him, email me and I can forward them to him and I can put you guys in touch. I don't know. This is awesome. Thanks, everybody.
Yeah, so I'll just put this, I don't know if it's still showing this last slide here. It's got my email address also if you want to send me a question. I think this is recorded or you'll have notebooks. So.
Yep.
Jared.Vasquez at Yelp.
Yeah. Edie's reading it. All right. All right, guys. Thank you so much, and I will see you Friday.
All right, guys. A lot of fun. So.
Have a safe trip.
All right.
I'll see you
Bye.
soon.